So for example, number 4, they're asking us to find the slope in the x direction for this rational function and then evaluate it at the points where x is 6 and y equals to -1. So don't worry about the z value because we're just finding the rate of change, so that's not going to matter. All they're giving here is the order triple that is on the surface described by this function. All right, well, so because we have variables in numerators and denominators. In some well, depending on the case, like in this case, we are differentiating with respect x. We can't differentiate the x cubed while it's in the denominator, so let's move it to the numerator with negative exponent. So you might argue, should we move the y to the numerator with negative exponent? No need, because in this case, the y is just going to be constant. We're not differentiating with respect y. All right, so that'll be f of xy equals to x squared over 3y, remains the same, plus 4y squared x to the -3. Alright, so in this case we're going to use the general power rule to differentiate x squared. The 3y in the denominator is just a constant, like having a 5, like having a 7, just whatever number. And in this case we're differentiating the x to the -3. This 4y squared is just going to be a multiple factor, a constant factor. Alright, let's find the partial derivative with respect to x. That is 2x over 3y plus, careful, -3 times 4, that's actually going to be -12y squared x to the -4, which will reduce to the following: 2x over 3y minus 12y squared over x to the 4. So that is our first derivative with respect to x. Let's evaluate it at the point where x equals to 6 and y equals to -1. So that is f of, not the partial, partial with respect to x at 6, -1. And then just substitute where it corresponds. 6 for x, -1 for y. 2 times 6, 3 times -1, minus 12 times -1 squared over 6 to the 4th. This is going to give us a really ugly number. That is, well, number 1, 2 times, okay, 6 over 3, that's 2 times 2, equals to 4 times the negative, that's -4. That's -1 squared, which is +1 times 12, that's minus 12. 6 to the 4th, big number, 1296. All right, and this reduces to, according to my calculations, 433 over 108. So just do this in the calculator and use the frac command. All right. So those were a couple of examples to compute partial derivatives and evaluate them and actually seeing the meaning of what we're doing in this case. All right. Of course, we can extend this to 3 or more variables, you know. For instance, if we have a function w, which is a function of x, y, and z. Remember how we defined the different functions back in the previous section? We can add more and more and more variables. Well, so in the case where we had two variables at the same time, we took the partial with respect to x, holding y constant. We took the partial with respect to y, holding x constant. So one variable at a time. So in this case, for a function w that depends on x, y, and z, if we differentiate with respect to x, then y and z remain constant. If we differentiate the function with respect to y, then it is x and z that remain constant. And lastly, if we differentiate with respect to z, then x and y are the variables that remain constant. Again, differentiate with respect to one variable at a time, and for a function of 93 variables, hold the other 92 variables constant. All right, that's it. Okay, let's have a look at one example to see this in action. So if we have a function of x, y, z, w, well, that's actually a function of 4 variables and not 3. It's 4 variables outputting an output that will be a fifth variable, which in this case f, the fifth variable, is the dependent variable, which depends on the 4 independent x, y, z, w. Alright, but well, they're asking us to differentiate with respect to w. Well, let's just move this w to the numerator so we can differentiate it. X plus y plus z, w to the negative 1, and then find the partial derivative of f with respect to w, that equals the derivative of w to the negative 1, which is negative 1 times x plus y plus z, w to the negative 2. And then, well, let's clean up the negatives and also the negative exponents, rather. So let me just write, okay, negative 1, or rather negative x plus y plus z, the negative accounts for everything here, over w squared. All right? Example number 6. So for example number 6, they're asking us to find the partial derivative with respect to the variable z for a function w or f that depends on x, y, and z. Alright, so let's discuss the potential differentiation rules that we're going to use. Okay, let's list them. Okay, what differentiation rules should we use for this one? Product rule is one, alright? So product. Any other rule? Chain rule, and well, it's not necessarily a rule, the derivative of sign, of course, alright? Okay, so the product rule, well, we already did a product rule before, so that'll be, okay, the partial of f with respect z. Okay, so that's the derivative of the first factor, z, and the reason why we're using the product rule, that's because we have a product between functions of that contain z's. If we were to differentiate with respect x, well, it's not a product rule, just a basic chain rule. If we were to differentiate with respect y, well, there's no y's multiplied, so no chain rule either, just another baby chain rule here, all right? So the derivative of z, which is 1 times sine of the same angle, xy squared plus 2z, plus the derivative of sine, which is cosine of the same angle, and by chain rule differentiate the angle with respect to z. So keep in mind that we will hold x and y constant, so the derivative of this term right here will be 0, plus the derivative of 2x, which is simply 2. But that's just the derivative of the v factor in the product rule. We need to multiply by z. Honestly, there's not much to do here other than cleaning up the 1 and multiplying to z and write it in front of the cosine here. Sound good? All right. And of course, I mean, you can make up your own functions, composites, radicals, add as many variables as you want, and have fun. All right? Have a lot of fun with this. Okay, so now let's go higher order partial derivatives, second partials, third partials, fourth partials. So also there's no limit as to what order derivative can you keep taking. I mean, of course, just go back to this pattern recognition when you differentiate sine or cosine. What do you get? After the fourth derivative, the fifth derivative takes you back to the original function. So those are just what we call four cyclic, if we will, derivatives. Or like the exponential, the derivative of the exponential is always itself, unless you have a different coefficient. We just multiply by that coefficient, you know. For instance, when you have f of x equals e to the ax, f prime equals to a e to the ax, you know. If you take the second, that would be a squared, a cubed, a to the fourth. So inductively, you would have the nth derivative to be a to the n e to the a x, right? So if you want to say, find the 97th derivative of f of x equals e to the 2x. So you would do f to the 97th derivative. That would be 2 to the 97th e to the 2x, right? Without having to go through the remaining 96 derivatives, you know? Well, that's not possible for every single functions. Just two functions like this that have like a repetitive pattern that just multiplies by a coefficient, you know. Some polynomial functions, for instance, depending on the degree, after a number of derivatives, after many iterations, what do you get? 0, 0, 0, 0, 0, right? For instance, a quadratic, a second degree polynomial, how many derivatives before you get all zeros? So that's going to be two derivatives, and then the third derivative is already, the third derivative and on, it's all zeros, right? So there's patterns that you know already, that you have seen before. All right, what about second partial derivatives? Higher order, but partial derivatives. Well, number one, the notation. Let's have a look at the notation, and then I'm going to do something crazy, of course. But first of all, how did we go back in Calc 1? So we started with a function, f prime, first derivative, second derivative, third derivative, and for fourth derivatives and on, you just use parentheses, for, and so on, right? We don't do for prime symbols. No, we do only up to 3, and then we put the number in parentheses. Likewise, okay, for the other notation, for this, well, this is for Lagrangian notation. For the Leibniz notation, that is, okay, the derivative of y is dy dx. And then for the second derivative, which we call d squared y over dx squared. This is to indicate that we're taking the second derivative. Now, what does that symbol mean anyway? This means that we are taking the derivative d dx, so we are applying the derivative operator to something that we already find its first derivative. All right? And then that means, even more, even better, okay, the third derivative, d3y over dx cubed. So we're taking the third derivative. So let's break this down. So I know this might look a little silly. It makes sense. It's just a bunch of symbols, but we need to get used to, we need to make sure we are comfortable with this, because when it comes to the partial derivatives, it's going to be interesting. Okay, so all right. So what about taking a third derivative means to take the derivative with respect x of something we already took the second derivative of. All right? And then just copy this, because this is the derivative with respect x of the derivative with respect x of something we already took the derivative with respect x. That is, first derivative, second derivative, third derivative, in this order, inside out. All right? All right, so how is that going to be related with partial derivatives? Well, so number one, when we take the second partial derivative, notice the notation, the partial derivative symbol squared of f over the partial derivative symbol x to the second, that's to denote the second partial. So here is the thing. In using the Jacobian notation, we're using the Jacobi's, d, and all that. Well, it's going to be in a slightly different, in a different order than if we did it with the Lagrangian function. So in this case, which is the shorter notation, we would just list x and then x. That means we're differentiating with respect to x, and we are differentiating a second time with respect to x. Same with, that is, take the partial of f with respect to x and take the second partial. So this indicates that we're taking the partial derivative with respect to x of something that we already took a first partial with respect to x. Same if we differentiate twice with respect to y. Now you need to be careful, because if you do, say, first with respect x, then with respect y, or vice versa, depending on the notation, you need to be careful with the order you write each one of them. For instance, so this is the symbol to find the derivative first with respect x and then with respect y. You need to notice how in this case we're doing this one first and then we do this one. Why? Because factoring out the partial derivative operator, what are we doing? Taking the partial derivative of something we first differentiated with respect to x, right? So first with respect to x, then with respect to y. Now, look at the Lagrangian notation. So here we read this notation from left to right. That one goes first, that one goes second. Now, let's have a look at the last example, or the last idea here. So, the partial derivative, the second partial derivative, that is, first with respect to y, second with respect to x, that is, in this direction. That means we do the opposite direction if we use the Jacobian notation, because we are taking the partial derivative with respect to x of something we already differentiated with respect to y first. So that means it goes in this direction. All right? All right, let me make something crazy here. So what if you had a function of x, y, z, all right? Some function of x, y, z. And we want to take the following partial derivatives. So f of with respect to z, and then with respect to z, then with respect to x. Maybe I want to differentiate 3 times with respect to y. Maybe I want to differentiate again 2 times with respect to x. Maybe I want to differentiate this function 3 times again, but this time 3 times with respect to z. All right? So that would be the order we would follow to go from left to right. First, twice with respect to z, once with respect to x, 3 times with respect to y, etc., etc. But when it comes to the Jacobian notation, we need to write it in the reverse order. Okay, how many derivatives are this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're finding the 11th partial derivative in parentheses. So I'm going to go I'm going to start from right to left. Number 1, 2 times with respect z, and then with respect x, and then 3 times with respect y, then 2 times with respect x again, and finally 3 times with respect z. Do you see the order? How is backwards? Just so you can see the difference between the two notations, because you may see something like this in other applications in physics, in chemistry. So when you are working with those Maxwell's equations in in electromagnetic fields and all that in your physics too, for those chemistry majors, when you're finding enthalpies, entropies, Gibbs free energies at different conditions, other than the ideal conditions, you need to solve differential equations to do those calculations, having the other constants, other numbers, and this involves finding partial derivatives of using those properties such as enthalpy, Gibbs free energy, and the like, that depend on volume, pressure, and temperature, and the like. So it becomes cool for those who are chemistry majors and are going to take PChem. So, yep, you will have a lot of fun. All right, so let's have a look at an example. Of course, maybe nothing as crazy as this. Of course, something nicer. Yep. Just so you can see the idea behind. Okay, find all second partial derivatives for the function f of x y equals to 3xy squared minus 2y plus 5x squared y squared. All right, so what are we going to do? Number 1, actually, you could think of a diagram, if you will. So you're going to have f. We will differentiate f with respect x and then with respect y. All right? So let's do this. Actually, this setup right here is going to help us visualize what's on the next section. That is the chain rule for multiple variable functions. All right. Okay. Let's find the partial derivative with respect x. That is first partial with respect x. Okay. The derivative here of 3x, that's just 3 times the multiple constant y squared. That's 3y squared. Oh, the derivative of negative 2y with respect x, since we're differentiating with respect x, y is constant, the derivative of a constant, 0. For the last term, the derivative of 5x squared y squared, well, we're differentiated with respect x, that is 2x times 5, that's 10x times y squared, that is 10x y squared. So that's the first partial. Okay? All right. So now let's find the derivative with respect y. Let's find the derivative with respect y. That is so the derivative of y squared, that's 2y times 3x, that's equal to 6xy. The derivative of negative 2y, is that negative 2? And the derivative of another y squared, that's just a 2y times the 5x squared, that's a plus 10x squared y. All right? Okay, so we're good with the first two partials, but that's not the question. Of course, we need to go through the first two partial derivatives to get to the 4 second partial derivatives. And again, let's go to that diagram. So now if we go to this branch, the partial with respect x, furthermore, we can go f with respect x and then a second with respect x. Or we can go f with respect x and then with respect y. All right? And lastly, if we go further through the other branch where we differentiated with respect y, okay, this splits into two more branches. First with respect y and then with respect with respect y. All right? That's how we're going to get the 4 second partial derivatives here. All right, let's have a look at these 4 partial derivatives. Okay, so this is what I'm going to do. I'm going to use these two results here to find the second partial with respect x, twice with respect x, which is this, f double x. So I'm going to use both notations, so you get used to the two notations, so you can see the difference. And, well, since it's in this case we're differentiating with respect, with respect x, this is a y term, that's a constant, that's 0. Here, the derivative of x is 1 times 10y squared. Right? 10y squared. Done. Now let me do the second, twice with respect y. That is partial of f with respect to y. That is f double y. F double y, okay, so the derivative of y is 1 times 6x, that's 6x. The derivative of 2, that's 0. The derivative of y is 1 plus 10x squared. All right? So that is our second partial. So we went, in this case, fx, fxx, and then we went fyy. Now we're going to get the two branches in the middle. So we're going to go f with respect x and f with respect y. So how are we going to connect this? Well, check this out. So let me connect this first, what we differentiated with respect x first. That'll be, we will differentiate with respect y. That's going to be this result from here. So that is with respect y, what we already differentiated with respect x. Okay, so what we differentiated with respect x here, now differentiated with respect y. Okay, this term right here, 6y, And the derivative of y squared, that's 2y times 10x, is that 20xy. All right. Oh, hold on. Give me a second. Nope. Let me use the other notation again. So that is fx and then y. All right. So that is our result. And lastly, I'm going to go fyx. That is what I already differentiated with respect y. Now I'm going to differentiate it with respect x. So that is, let me connect it over here and let's show this. Okay, so we will differentiate with respect x what we already differentiated with respect to y. That is, in the opposite order, fyx. That is, okay, this first derivative with respect to y, I will differentiate it this time with respect x. That is, the derivative of 6xy, that's just the derivative of x, which is 1, times the remaining factors, that's 6y. The derivative of 2 is 0. The derivative of x squared is 2. X times 10y, that's another 20xy. All right. Do you notice anything interesting about our results here? What do you notice? The same. What's the same? The last two, the fxy and the fyx, they're the same, right? They're the same. Well, actually, this is there's a theorem for that. Let's describe this theorem. It's called Clairaut's theorem. So that's also known as the mixed partials. Okay, let me write that down. Okay, mixed partials. So that's the what are those mixed partials? So the mixed partials are obtained when we differentiate it with respect x and then y and vice versa. So Clairaut's theorem is about this, that the mixed partials are equal as we got it in the previous example. All right. So let's have a look at an application of this Clairaut's theorem with this function of 3 variables, by the way. So we're given f of x, y, z equals to y to the x plus x ln of z. So they're asking us to show that the two mixed partials are equals. That is, the partial with respect x and then z is equal to the partial with respect z and then x. Okay, so this is the Jacobian notation. So that means this is, essentially we want to show that fxz equals fzx, right? Again, we're going in this order, right? We're going in that order, the opposite direction. Okay. All right, let's find the partials. So, fx, the first partial with respect x, okay, the derivative of y e to the x is itself y e to the x plus x, the derivative of x ln z, that is the derivative of x, which is just 1, times ln of z, that's ln of z. And then the partial with respect z, that is, in this case, y e to the x does not have any z's in it, so that's a constant, that's going to be 0. Here, the derivative of ln of z is 1 over z times the variable times the variable x, the factor x, that's simply x over z, which I will write it as x times z to the negative 1, because I will need to differentiate this z later. Okay. All right. So now let's take the remaining. Well, actually, I'm not gonna do fxx and fxz. fxx and fzz, because we don't need them. We only want the mixed partials. That is, f with respect x, then with respect z. That is, this quantity right here with respect z. And again, this is going to be 0. the derivative of ln of z, that's 1 over z. And over here, the derivative with respect, so f z, then with respect x, the derivative of x, isn't that just 1 times 1 over z, that equals 1 over z. Oh, are these mixed partials equal? Yep. So this function satisfies Clairaut's theorem, or well, actually gets Clairaut's theorem verified. Not that it's satisfied, it's verified. All right. Well, of course, this Clairaut's theorem can be extended to higher orders, higher order partial differentiation. You know, we can find mixed partial derivatives. So we have different orders for to differentiate. So if we have a two-variable function, there's only two possible orders, right? X, Y, Y, X, right? Which is what we have here. But what about when we have three variables? So if we have X, Y, Z, well, we can do X, Y, Z. We can do 6 total orders of differentiation. X, Y, Z. Well, actually, f x, y, z, f x, z, y. Then we could do, if we start with y first, we can have x, then z, and zx. And if we start with z, then we can get y with x and x with y. So that is a total of 6 potential order of partial differentiation for 3 variables for the third order. And it turns out these are all going to be equal. So, but well, we're not going to verify 6 of them. We don't want to take too many derivatives. It's just enough to show these 3. That is the third partial. That is, okay, in Lagrangian, let me translate this to Lagrangian. That is f with respect x, z, z, it's equal to f z x z, this direction, and f z z x. All right. Well, of course, we're going to use the results from what we had before, from part A, to show this. Okay, so let's find f x z z. All right. All right. So f x z. Do we have f x z? Isn't that this guy right here? Let me write it as z to the negative 1. Also, this one z to the negative 1. All right. So we can differentiate this. Okay. So we are asked to differentiate z to the negative 1 with respect z again. That is negative 1 z to the negative 2, which is negative 1 over z squared. All right. Let's do the other one. F z x z. All right. We already differentiated f with respect z and then with respect x. That is the second mixed partial from part A, which is also z to the negative 1. Well, I'm not going to differentiate it. I'm just going to give you the result because it's the same function. That's a negative 1 over z squared. All right. For f z z x, we would need to find the derivative with respect z twice and then differentiate that with respect x. Okay, so let me go back to the very top of the problem where we differentiated once with respect x. What did we get? We got x over z, which is x z to the negative 1. So this guy right here, I'm going to differentiate it a second time with respect z. That way we can differentiate it a third time, but this time with respect x. Okay, so the derivative of this with respect z, that is x, negative 1 x z to the negative 2, which is the same as saying negative x over z squared. All right. Then I'm going to use this result right here to differentiate it with respect x. look at this expression. What's the derivative of x? Times negative 1 over z squared? Negative 1 over z squared. Is that verified? Yes? It better. If you didn't get to verify, double check your calculation, double check your differentiation rules, etc. All right, applications. Let's have a look at a cool application to chemistry in the next page. Okay, so the volume in liters for a certain mass of an ideal gas is related to its pressure in millimeters of mercury and its temperature T in degrees Kelvin by the law of V equals to 30.9 T over P. Well, so let's have a look at this equation. So ideal gas, what's the ideal gas law from chemistry? PV-nRT, right? Well, how is this PV-nRT related to the equation we have in our problem? Well, if we solve that equation for V, for the volume, we get nRT over P. Well, what is this 30.9? Well, that 30.9 is the combination of multiplying some n amount of moles of an ideal gas times the universal constant for gases depending on the system you're working. 6.82. Oh, I forgot the number. 8.134 or 341, something like that. 6.082, right? I think it's 1, right? When you have it in liters, atmosphere. Oh shoot, I'm a chemist and I forgot that constant. Anyway, so I need to review a little bit of that. So, well, that's just a combination. Maybe you have 5 moles of neon gas, hydrogen gas, whatever, and we'll just multiply by R. There you go, right? So, well, they're asking us to find the partial derivative with the volume with respect to temperature and with respect to pressure when at the instant when the temperature is 100 and the pressure is 200. So, and we will interpret the results. So in a similar way so we're getting like the slopes in the x direction and the slopes in the y direction, but for the application is the slope in the temperature direction, the slope in the pressure direction. In other words, the rate of change of the volume with respect the temperature when holding the pressure constant, and otherwise when the rate of change of the volume with respect the pressure when the temperature is constant. Well, let's get this. So I'm going to rewrite this equation. 30.9 T P to the negative 1. Yeah, I remember that. I just recall. It's 0.082, not 6.082. Yep, 0.082, the R. Anyway. All right, so the partial of the pressure, partial of the volume with respect the temperature. Well, the derivative of the temperature, which is just 1 times the remaining factor, that is 30.9 P to the negative 1, which is simply 30.9 over P. And then let's find the partial derivative of the volume with respect the pressure this time, that is negative 1 times 30.9 T P to the negative 2, which reduces to negative 30.9 T over P squared. Alright, so these are our partial derivatives of this ideal gas setting with respect for where the volume is the dependent variable and temperature and pressure are the independent. Well, depending on the situation, you may want to control volume and pressure, and the temperature would be your dependent variable. Or you may want to control volume and temperature, your pressure would be your dependent variable, depending on the setting, depending on the lab, depending on the experiment, right? But now we want to evaluate this. Let's find the partial of the volume with respect to the temperature at the instant, or when the temperature is 100 and the pressure is 200. All right, that is 30.9 over P, which is in this case 200, and that is approximately 0.2. We will take care of the units in a second when we do the interpretation for this, okay? Don't worry. What's next? So that's the partial of the volume with respect the pressure when the temperature is 100 degrees and the pressure is 200, what was that? Millimeters per mercury, right? Yeah, millimeters of mercury. Okay, so that'll be equal to negative 30.9 T, which is 100 over 200 squared. Using our calculator, that should give us approximately negative, careful with signs, 0.077. So these are our results, our numerical results. We need to interpret this based on the context of the situation, which is again the ideal gas situation. So what does that mean? So let's interpret the first result. Let me change colors. Okay, so the first result is telling us that the volume of a gas increases at a rate of 0.2, what are the units? 0.2 liters per Kelvin. All right, liters per Kelvin, because look at the variables in the partial derivative are volume units per temperature unit, so liters per Kelvin. When T equals 100 and P, the pressure, is 200 millimeters of mercury, and when the pressure is constant. So that is the interpretation of the first result. All right, let's have a look at the interpretation of the second result. So this means that the volume of a gas decreases. How come decreases? That's because of the negative sign in the result. It decreases at a rate of 0.077. Notice I didn't write the negative sign because the word decreases already implies that the rate of change is a negative number. So if you write decreases at a rate of no, it's redundant, right? Actually, it's like canceling sign. Negative, it's positive, and it doesn't make sense to decrease at it's positive, right? So 0.077 liters per millimeter of mercury that you increase of pressure when T equals 100 Kelvin and the pressure P equals 200 millimeters of mercury, when the temperature remains constant this time. All right. Well, just to make sense out of this, I mean, you can try this at home if you want, because just inflate a balloon, a regular balloon, and have a look at the change of the volume with respect to temperature. So what happens when you heat a balloon? Just don't put it too close to the fire, otherwise it's gonna pop. You just put it inside hot water. That would be a that would be a safer experiment? Well, when you increase the temperature of a gas, the volume increases. That's because, well, this temperature makes these gas particles to have more collisions and try to go anywhere, and that increases the volume. Now, what about the change of the volume with respect to pressure? Well, how can you change the pressure of a gas? Well, just press the balloon, right? So what happens when you press a balloon? When you increase the pressure, it gets smaller. That explains the negative sign. It gets smaller. It decreases. All right. So rates of change, partial derivatives, more functions of more variables. In this case, well, a cool application to chemistry. All right. All right, do we have time for one more? Yes, sure, we do have time. Well, let's have a look at finding partial derivatives of functions defined as integrals using the infamous second fundamental theorem of calculus. Well, so here's the thing. We're going to be given a function f of x, y equals to the integral from x to y of 5t to the 4 dt, and g of x, y defined by this integral of from x of e to the t squared dt from xy all the way to x squared plus y squared. So I already prepared you in a way for this applications of second fundamental theorem with take-home quiz you submitted yesterday for the arc length. So, but in that situation, when you had the derivative with respect t from 0 to u. What was that? From 0 to t. So that's f of u du. That's simply f of t. All right. That's the second fundamental. That's when the limits are. It's just a constant, and the variable it's just t. I'll show you how is that going to work when it's something more elaborate, like with powers like the one we have here. Okay. So let me do. So the partial derivative of the function y with respect of the function f with respect y. Well, so here is how we're going to take the derivative. So take the derivative with respect y of the integral from x to y of 5t to the 4th dt. I know this one is a polynomial function. You can easily integrate 5t to the 4th to get t to the 5th. Agree? However, I'm going to take a different approach because this is going to help you visualize the differentiation of this crazy one. All right? Because it's going to get a little crazy. Well, suppose this 5t to the 4 is just some function f of t. In the end, that's what it is. Okay? From x to y, that's f of t dt. So here is the thing. Ignore the limits of integration. Ignore that we are doing another differentiation after integrating. Let's recall that whenever we integrate lowercase f, that gives us big F of t. Right? Remember that fundamental theorem of calculus? Little f goes to big F. Differentiate, big F gets back to F. All right? But in this case, we will integrate between x and y. Keep the partial operator. That is f of y minus big F of x. All right? Okay, so let's take the derivative again. So we went from little f to big F upon integration, but now we're going to take a derivative again. So those big F's are going to become little f's again. All right? So this is what, careful here. So partial of f, so with respect y of big F of y, minus the partial with respect y of big F. Okay, so here is the thing. Big F of y differentiated with respect y. Isn't that going to become simply little f of y? Big F becomes little f. But what about here? Some function that contains only the variable x, nothing else. So this is what this big F of x indicates. It's any expression that contains x. what happens when you differentiate this with respect to y? The derivative of a constant is 0. So just f of y. Alright? So this is our f of t. Now just write f of y, replace the t with the y. Alright? So that is our partial derivative. Okay? Alright, let me skip part B for now and let me show you. Do we have time? Yes, 2 more minutes. Yeah, let me do. No, you know what? Never mind.